We need to learn how to find the minima of energy in the case of deformable bodies, but we will do it slowly. You should go to my website and look for a paper of 2013. The first author is Prof F, and then I am the second author, and then there are many other authors. You download this, the PDF. This paper, I will explain you how, is a paper in which I was obliged to write because of the questions of my students in analytical mechanics when I gave the classes 3 years ago. So you should find there a lot of details of what we will do now on. Okay? We will talk about the file. I have not understood how to send to the file, so we will discuss about the other books. So we need to discuss some technical things because it is useless if we go too quickly ahead without understanding what we are doing. Okay? But all calculations which we will do now are written in that form. So what happened to me is that I discovered that my students were asking me a question for which in literature there was no answer. So I was obliged to find the answer. We start with a vector. We have two kinds of vectors. We have material vectors and displacement. So, in the reference configuration, you have one material point, another material point, and the vector which goes from x to x bar, and this is a material segment or a material vector. And we try to denote these vectors with capital letters. Then we have in the actual configuration one position, another position, and the displacement from the first position to the second one. So this one is the position, small x is the position of capital X. And small x bar is the position of capital X bar. So, you have to understand that this is a segment of material particles, and this is a displacement between one point, the position of capital X, and the other point, the position of capital X bar. Of course, what can happen is that this segment has this shape in the actual configuration. Because if the body is deformed, this segment can become heavy. Okay? Take a body, paint this red. Okay. You take a body and you paint a segment red. Then you deform it. What will happen? This body has now this shape. Whereas points, you have a deformation. So this is the set of positions occupied by the material points in this segment. Okay? This is the position of cardinal x. This is the position of cardinal x bar. This is the displacement from the first position to the second. So this is the vector which I need the shortest path from this point to this point, from this position to this position. And the material segment here is a set of material points, and their position can be every, depending on how your body is deformed. Okay? Of course, when V is small enough, so if you take a rather small segment, then the tangent of this curve becomes a good approximation of the shape of the curve in the actual configuration. And this is the reason for which we try the Taylor expansion of K of x. Okay? So, if you usually in the books, all this is implicit, not explicit. So if you have epsilon capital V, if the norm of V is 1, if the norm of V is 1, this is a finite segment. And so this can happen. Okay. If epsilon is small enough, then the vector V epsilon V equal to F epsilon capital V, which is this small vector here, is a good approximation of the shape of this small segment in the actual configuration. As F is linear, epsilon goes out, simplifies, and you, people who are writing books are lazy, so you get F equal FV, and you are lost because you miss the fact that this vector is different from that vector. So why I am spending all this time for telling you these things? Because you must learn to read the books, reconstructing what is not said in your mind. This means becoming independent. Okay? So, of course, this equality is not a true equality. Here, you have infinitesimals. Okay? But we neglect these infinitesimals in general. Okay? Good. So, we must now learn how to manipulate these vectors and these linear applications. So to invest some time in representing vectors in components, I hope that you have an idea of these things, but in any case, we try to be self-consistent. So, we take a vector V, we choose a basis in the actual configuration, and this vector V can be written as sum over I of the component Vi times the vector Vi. This is a quick way for writing this long formula. These two formulas are exactly the same. Okay? So, I am bored, I don't want to write this, I write this. It means exactly the same thing. Okay. Then, we are lazy, but as Einstein did it, we can do, instead of writing this formula, we can write this formula using so-called Einstein convention, which means wherever you have the same index repeated 2 times, summation is meant. Okay? So this is for doing calculations in a quick way. Okay? Of course, you are not worried, I hope, by this word. I can change the name of the index. I hope that you have an experience with programming languages. If you have a for or a do cycle, you can change the name of the variable in the cycle, nothing happens. Of course, never write 2 commands for with the same index. If you have 2 iterations, you must use different names for the different indexes. Okay? So one has to be careful in choosing the names of the summation indices. Okay? Now, this formula tells you that once you have chosen the basis, so if you have chosen E1, E2, and E3, maybe it is worth to tell this again. This formula means choose for I1, choose for I2, choose for I3, and then sum this product. Get this number. What is telling this formula? Choose for J1, choose for J2, choose for J3, you get the same. So the fact that you have changed the name of the summation index is not changing the value of the final result. You can call this Bacca, H. You can call it as you want. The final result is the same. Okay? And I'm sure that you have seen this. If you have a common, do I equal 1n, and then here you write a sequence of orders, and then you have the end of the do cycle. It works if you change I and you call it H. What is important is the range where this index can vary. Okay? This formula in this form has been written by Levi-Civita in his master thesis. He invented this notation while writing the master thesis. If you check the works of Gabriel Viola, who didn't know this powerful tool for doing what you will do with us in 3 hours, the poor Viola needed months and wrote several hundred pages of terrible calculations. It is unbelievable how he could manage to go ahead. What you have to understand is that the right formalism is always 90% of the work necessary for getting a mathematical result. When you formulate a problem in the right way, you know, in Alice in Wonderland, Alice is asking to the crazy hat maker at a given moment, which is the answer? And the hat maker says, which is the question? You must ask the right question for getting the good answer. So if we ask ourselves the right question, the answer will be very easy. And in order to calculate what we need to calculate, the equilibrium equations for a deformable body, the questions must be asked in the correct way. So you have to be patient enough to understand this formalism. Okay? But we will practice slowly. I think that this is such a powerful tool that if I only manage to teach this, your visit here is worth it. Okay. Of course, in engineering schools, somebody using this formalism is considered a crazy mathematician. So be careful in talking about these things to other people. It is a secret of, it is an esoteric knowledge. Okay, we keep in our secret group. Then you can tell to people the final result without explaining how you got it. And then it is their business. Now, we don't have only one vector space. What is very important to understand is that here we have 2 vector spaces. We have the vector space of material segments and the vector space of displacements. Okay? They are 2 different vector spaces. And so I have written here the linear combination in terms of a basis of the vector space of displacement. Of course, if I have a capital V vector, then I can write summation. Okay. Then we prefer to change the class of indices. Everything is capital. So instead of using small indices, we introduce capital indices. So A from 1 to 3 of capital V A, capital E A. So we represent every material vector as a linear combination of the basis of material vectors, capital E. Okay? Or, if you want to use the Einstein notation, we have this formula. Okay. I could now try to talk about a complex technical concept, contravariant and covariant components of a vector. We elegantly skip it by assuming that capital EA and small EH are orthonormal bases. Okay? But I want to give you the names: contravariant, covariant components. Because if you want really to master this theory, you must learn this concept, which is written in the books I will give you. Okay, so my suggestion is that you should eventually learn this thing. There is covariant, contravariant. You know, when I was in Poland in '88, I could not say to my colleagues at IPPT1 that Kaczopol had proven the theorem of Banach before Banach, because you are very nationalistic, okay? But there is no Polish scientist who understood covariant and contravariant components and way of changing of components with the change of the basis before Levi-Civita. So this is typically Italian intellectual result. Of course, somebody could say that Levi-Civita was Jewish. Okay, but Levi family has been in Italy since the epoch of Roman Empire. So they are culturally Italians. Okay. Now, let's go ahead. We can do a quick calculation which will become very useful. F of capital B. This is a linear F. You apply to capital B and you get a vector small v. Okay? So what can you do? You apply F to V, A, E, V, which is the representation of V in the basis EA. Okay. And then you write this as VI, EI. Okay? This is a linear map. I'm telling you something very simple. But I think that these things need to be understood one time in the life. Okay, so they are very simple, but they give you a powerful notation we will use systematically. So, this is a linear combination. F is linear, so this comes out. V, A, F, E, A, equal V, I, E, I. Okay? So this V is coming out. F is a linear application, a linear map. So this is 2. So this is equal to F, E. Okay? Okay. Then we introduce another small notation. We introduce Kronecker delta. Kronecker is the only person who managed to get very close results to those of very children. Omega delta is a matrix with two indices. When the two indices are equal, it is 1, and when the two indices are different, it is 0. Okay? So if you have an orthonormal basis, this equality is true. So Ej dot Ei equal delta Ij. So if we calculate the inner product of this animal here and this animal there, remark that now this is an Eulerian vector, because capital EA is a Lagrangian vector. F maps Lagrangian vectors into Eulerian vectors. Okay? So VA F EA dot EJ equal VI EI dot EJ. Okay? So at the end of the story, this is delta Ij. So the only surviving Vi here is Vj. We have to learn to do these things, so we do it slowly. Okay? Here you have summation over I, no summation over J. Okay? So let us start doing this. E1, E1. Okay? Of course, if you do this way, you must repeat it 3 times, because you have to write E2 and E3. But, you know, young people need to touch difficulties. So, let us start and say, oh, I choose E1. Okay, so here, E1 dot E1 is equal to 1. So you get V1. Then E2 dot E1 is 0. E3 dot E1 is 0. So here the only surviving animal is V1. Okay? This is equal to VA F EA dot E1. Okay? Then, what is doing 1 differently if you compare it with 2? Nothing different. So here, you can write E2, and here you get V2 equal VAF EA dot E2. Okay, if you read the book of Piola, you find 1,000 equations, and after a while, he writes words like, what we have done for 1 is also true for 2 and 3. So he writes this formula, and instead of copying for 2 and 3, he writes down integer which is a beginning of the modern notation. Okay? But it is rather difficult to imagine it. Indeed, you know, sometimes in writing, I cannot write all these formulas in this word, so the reader will write them by himself. Okay? Now, think how clever it is instead to say, take J spanning 1, 2, 3, and you have written all formulas. So this is the powerful tool we have now in our hands. Okay? Now, this animal we can call F. So this is the definition. Now, let us try to understand what we have done. We have invented a matrix. Because when J and A vary between 1, 2, 3, you get the entries of a matrix. This matrix has a magic action. You calculate these products, you sum up on repeated indices, and what you get? The components of the image of the linear application in the basis EI. So let us think what we're doing. Okay. You give me two bases, E, I, and capital E, A. One basis of the first vector space and another basis of the second vector space. Once you have fixed the basis, you know the components of every vector. So, if I give you the basis, you can calculate the components of every vector. Those, somebody can think that the components of a vector are characterizing a vector? Yes, only if I tell you the basis. So I can draw something only in a plane, but if I have this vector and I have this basis, the components of this vector geometrically are these two projections, right? I keep the same vector blocked, and instead of this basis, I choose these other bases. The components are different, right? So tells you that all this discussion is empty mathematics. Because I know the components and I can treat my theory with the components. It is either stupid or is pulling your leg. You cannot discover which is the correct vector only if they give you the components. You must know the basis also. So you must know the basis and the components in order to specify a vector. So once, if I give you 3 components, in order to construct the vector, I must give you the basis. Okay? This is crucial. Now, if I give you a linear map is something which is associated to every vector, another vector. What we have discovered? If you block the basis EA, capital EA, and if you block the basis small ej, then you have a matrix. This matrix is doing the job of the linear application. What is doing? You give the component of the first vector, capital V, in the first basis. To calculate the row times column product, and you get as a final result the components of the image in the second basis. Wonderful. But if you change the basis, one of the two or both of them, this matrix is changing. Look, if I change E, capital E or small e, these numbers are changing. So not only the vectors have components which are changing with the change of the basis, but also the representative matrix of a linear application is changing when you change the basis. Okay? Now, do you believe that the law of physics cannot be written in different way if you change the basis? This is Galilean invariance. Law of physics are independent of the observer. So if you write the law of physics in terms of components, you are blind. Because you cannot easily express the invariance, Galilean invariance. So the reason for which we must talk about a vector space, another vector space, a linear map from one vector space to the other vector space, is that in this context, Galilean invariance or invariance for change of observer is much easier to be formulated. Okay? Of course, we need to do some calculations. We need to proceed in estimating some quantities. In this case, we introduce the basis and we do the calculations. Okay? Okay. So, usually, you know, my professor of rational mechanics came one day and started doing calculations without telling anyone. He gave us a book and he said, okay, you study it. So it's like pushing somebody in the water. If he swims, he's swimming, otherwise he dies. Okay? I tried to give you the ideas, but now you must be patient and you must demonstrate slowly these ideas. Okay? Okay. Let us move another step. So now on, I will use when needed these formulas. Okay? If I have the inner product V dot W with this notation, again, I could be more precise, but I will not. With this notation, the inner product can be written in this way. Delta ij is 1 if the two indices are equal. It is 0 on the one. Okay? So this is the inner product which we know already in the new notation. Okay? Now we have introduced f v dot f w. You remember yesterday? This angle minus v dot w. This was measuring, if you ask v and w to vary in the space of material vectors, this is giving you the deformation measure. Okay? This is the same as we wrote yesterday. Write this. Okay, remember? Okay, I want to talk a little bit about this inner product. So you have f v dot f w. Do you remember we said what is the transpose of an application? We have the matrix capital A applied to the vector V dot W. This is equal to small A transpose W dot V. Okay? The transpose is jumping to the other side. So we write this in components using the calculations we have done up to now. So W I A B J delta I J. This is the first inner product. This is equal to Wi okay. I have written A applied to capital A with a magic formula I have painfully found for you. Okay? I'm doing these calculations because you need to become a little bit experienced with this notation. before we do the calculations we need to do today. Okay? Okay. Then this is equal to, I can write J instead of I, because this animal is always 0 except when J is equal to I. Okay? So this is Wj this is summation over repeated indices. Okay? Then I write A transpose W. This animal has an index. Now I must be careful in choosing the indices. So let's choose C, different from the others. VD delta CD. Okay? So A transpose C H WH. What is this? This is the representative matrix of the transposed application in the basis we have chosen, the component CH. Okay? Then you have V D delta CD. Okay? But delta CD, this, if you have this summation applied, delta is 0 except when C equal D. So we can write A transpose CH WH, and then you have V C. Okay. This animal has to be equal to Wj these two animals are equal. Okay? Now, this summation, I can change the index and I can call it C. It is the C. This summation, I can change the index, I can call it H. Okay? This equality is true for every W and for every V. Okay? So this equality is true if and only if the matrix which is representing the transposed application A is the transposed matrix which represents A. So this is the reason for which they are teaching you the transposition with the matrices. Okay? Now, this inner product, we can calculate it in many times, in many different ways. And we start doing with different techniques, because this is very important. So we can write V dot F transpose F down, because F can jump to the other point. Okay? Now, the representative matrix of F is Fia. The representative matrix of F transposed is, we have calculated before, is obtained transposing the indices, but the matrix is always the same. Here you have a summation over I. Okay? So what you have done, you have built a matrix whose indices are only capital. And indeed, F is mapping the material vectors into a Eulerian vector. F transpose is pulling back a Eulerian vector to material vectors. This animal is a linear map which takes a Lagrangian vector and is transforming it into another Lagrangian vector. Okay? So this CAD is called Cauchy-Green tensor. Is a tensor which is mapping material vectors into material vectors. So, C minus identity, 1/2, we have called the deformation tensor. This identity, how you write this identity? You write it delta AB. Because this is the identity in the Lagrangian vector space. While when you have the identity in the Eulerian vector space, you will write delta ij. Okay? Now, you can decide that the deformation energy value, we call it epsilon. We said that epsilon depends on G. So we said, so we conclude our discussion preparing the calculations you will do in the next block, in the next lecture. E of G is the energy which is needed in order to deform the unit cube of your deformable body. You remember, if I have a spring whose length is given by x, and if I change the length of this spring, the rest length being 0, for simplifying our reasoning, or you could say that rest length is x0, so we generalize completely what we need to do. Okay? So you have a spring whose rest length is x0, which is the deformation energy of this spring if it is linearly elastic. It is 1/2 the elastic coefficient k times x minus x0 squared. Okay? In the case of the spring, you have only one scalar quantity which is measuring its deformation. And this scalar quantity is given by x. You change x and you have another energy. Okay? So this is a way for measuring the deformation energy of your spring. Okay? Now, technically, you can understand this. I don't have one number measuring deformation. I have a tensor. A symmetric tensor, G. And this tensor, if you have chosen a basis for the vector space, Lagrangian vector space, this tensor has the component GAB. So the deformation energy must be a function of all these variables. Of course, this function depends on the basis. If you change the basis, this function will change. Okay? So once you have fixed the basis, you have a deformation energy. Like this. Okay. Now, for preparing the work of Luca Placidi, I tell you that actually G is a function of F, because G is F transpose F minus N. For some reasons, it will be easier to consider another function of F for doing some calculations. Okay? So I want to underline that as G is a function of F, we know that the energy must depend only on G. But we can consider the composed function E bar of F in this way. Okay, because we know that G of F is F transpose F minus the element 1. So for some calculations, we will consider the deformation energy as a function of F. Okay? I want to tell you that I could try to sell to you all these things, telling that this is the book, the manual for COMSOL. Actually, COMSOL is working using this theory. So I could, following the modern trend, to pretend that we're not studying a theory which is very old, is valid notwithstanding COMSOL. You know, we used Abacus, we used Nastran, we used COMSOL. The software changed, the theory is always the same. If somebody tries to tell you that this is the manual of instruction of COMSOL, when another software will be born, you can believe, I'm lost. I must learn everything again. It's not true. The interface between you and this theory will change. But the theory itself is always the same. This is something in which modern universities are losing. You have to teach to students what will be useful after 50 years. And you must leave to the students to adapt to the temporary software which is used in that moment. Why? Because when I was young as you are now, the computer of the Wood University of Napoli was less powerful than this one. And it was occupying 3 floors of a building. And in order to give orders to this computer, I needed to punch some cards. This theory is always the same. So, in the short life of a human being, we have experienced an enormous change in the tools for doing calculations. But the theory, which is behind the calculations, this is much more stable. If somebody has said me practically, I mean, I teach you how to punch cards, after 5 years, I were lost. So when you will learn COMSOL, you learn it, you are happy, you see some results, you can produce beautiful movies, but you must understand what is behind. What is behind? A deformation energy, for instance. Now we need to teach you how to manipulate deformation energy to get useful equations. Okay? Okay, now we must talk a little bit about how finding minima. This you should know already, but I need to prepare what will be said to you by Luca Blasiuk. So before we stop, we need to talk about this. Okay, we'll come back to this many times. Again, what I'm telling you is the final result of the work of an Italian genius. I'm talking about Lagrange. So let us start with an interval A, B of real numbers. By the way, usually the students, when I'm talking about this, show a face which is happier when compared with the calculations I did with indices. What I'm telling you now is much more difficult. Much more difficult. You believe to have understood it, simply because they repeated it to you many times. The indices notation is a game for children. This is much more difficult. Okay? Consider a real valued function defined in this interval. And decide that you want to look for maxima and minima of this function. So what they are teaching you? They are teaching you that you must calculate a derivative. Okay? So they tell you, take the function f of x, calculate its derivative, and look for the points in which this derivative is vanishing. Your faces are calm. You are simply accustomed to this. Okay? Now I want to tell you that this is not exactly true. Why? This is clearly a maximum, and the derivative is not zero. This is clearly a minimum, and the derivative is not zero. Here you have a minimum, and the derivative is zero, and here you have a maximum, and the derivative is zero. However, there are some very bad functions in which the derivative is zero, which have zero derivative somewhere, and in the point where this derivative is zero, you don't have neither a maximum nor a minimum. This is not a strange function. This is x cubed. A neatly innocuous function. Okay? But I want to be a little bit bad with you. I thank my professor of mathematical analysis for having taught me difficult things. Because when studying that terrible fiber reinforcement material, I found a problem which is a nightmare. Consider the function square root of absolute value of x. This function is behaving like this. Okay? Try to calculate the derivative here. There is no derivative in zero. But this is a minimum. You know, these very bad fiber reinforcement materials have an energy which is behaving like this one. So, for 20 years, people tried to calculate derivatives. They couldn't find. they tried to use console, which doesn't work. Why? Because the theory behind console is a theory based on a generalization of the calculation of derivatives. So if you do not know what you are doing and why you are doing it, you will soon find a problem which is not fitted in the theory which you are blindly applying. I remember that Federico Cafiero was violently attacked by his colleagues. They said, "You are a crazy mathematician. What you are doing is useless, practically." Okay? He didn't mind, and he kept teaching us these degenerated cases. I needed this degenerated case many years after in order to attack a problem which is very useful for designing modern airplanes. So what I want to tell you is that when we are teaching and when you are studying, especially if you want to start a PhD program, you should not limit yourself to the solutions available for already solved problems. You need to open your mind and to understand which are the limits of application of the methods which you are using. Because most likely, next problem will need new methods. Okay? So, in this moment, I'm using a PhD student with a master in mathematics together with a postdoc with a master in engineering sciences. No, two postdocs. For solving this terrible problem, which has been called the nightmare of Pipkin. Pipkin was a professor at Brown University in the 70s. He didn't manage to solve it. As I'm crazy, I decided to solve it. Okay, now let's go back to our standard case. How do you prove that a point where you have a maximum and a minimum has zero derivative? Because, by the way, this reasoning I'm telling you now has been conceived by Lagrange when he was 16. Of course, he had very good professors. He was studying in the school of Jesuits in Turin. He had exceptional teachers. Okay, but he produced this result when he was 16. Okay? I write Taylor expansion in the neighborhood of x0. So I consider x0 and I consider a small neighborhood of x0. And I write Taylor expansion in this neighborhood. I'm sure that you have studied the remainder of a Taylor expansion, the Lagrange remainder of a Taylor expansion. Tomek, can you tell it in Polish? Remainder. How do you tell in Polish remainder in a Taylor expansion? I'm sure.
Yeah, it's the rest of the okay. Yeah, I got in Polish.
In English, I'm sure they call it the remainder,
Yeah, that's
which is this element here.
That's also in Polish. To jest pozostałość, czyli to jest człon, który jest mały. Jeżeli rozwijamy szereg Taylora, to zawsze bierzemy kilka wyrazów i potem pozostają wszystkie inne, które pozostały, są dostatecznie małe, że je możemy pominąć.
Lagrange found an expression for this remainder. He said, there is a point psi such that this remainder is equal to the second derivative of f in psi times 1/2 times x minus x0 to the square. So you find always a psi of x such that this remainder is exactly given by this. Okay? Of course, you need a second derivative. Calculate the second derivative of the square root of absolute value of x. You have nothing like that in that degenerate case. Okay? So assume that x is so close to x0 and that the function f is regular enough that this remainder can be neglected, and this is nearly equal to this. Okay? Then you can write f of x minus f of x0, and this is nearly equal to f prime x0 times x minus x0. This we can call, I'm preparing the work of Luca, this we can call delta x, the small variation of the independent variable in the neighborhood of the point x0 where you're looking for maximum or minimum. Okay? So, we call this delta x. Okay? And of course here you have f x0 plus delta x minus f x0 nearly equal f prime x0 delta x. So what you are doing, this is the genius of Lagrange. The genius of Lagrange is the following. I consider the independent variable. I change it a little bit. I consider the variation of the dependent variable, and I approximate this variation with a linear function of delta x. We can call this element the first variation of f in the neighborhood of x0. Why first variation? Because you are neglecting the remainder. Okay? Now, what happens if f x0 is a minimum for it? If f(x0) is a minimum, this animal will be always greater than f(x0). So, if I am here and I change a little bit x, I get greater values. So this difference is positive. Or 0. Okay? Of course, I will never forget that here I have some remainders. Okay? This is nearly equal. When I neglect higher of the infinitesimals, but it is equal. But the true equality ones are remainder there. Okay? Okay. Now, this animal is positive. When I go very close, the remainder is negligible. Delta x can be positive or negative. If I am on the right, delta x is positive. If I am on the left, delta x is negative. So this animal here can have either a positive sign or a negative sign. So imagine ab absurdo that f prime x0 were positive. You choose delta x negative. And this inequality is not verified. Then f prime has to have negative sign. But then you choose delta x positive and you get another absurdum. What can you do? F prime has to be 0. This is the only possibility. If f prime is 0, then the first variation is vanishing, and you are left with the remainder. So this difference is equal to the remainder. You remember how the remainder we wrote? There was x minus x0 squared, which has always a beautiful positive sign. So, if the second derivative is positive, you have a minimum. And if the second derivative is negative, you have a maximum. So, how do we look for maxima and minima? If you manage to estimate the first variation, I calculate the first variation, and then I impose it is equal to 0. Okay. Now, the greatest result obtained by Gabriel Viola in his memoir of 1822, which was another time his master thesis, is the following. He said, I will write the deformation energy for a body. I calculate the first variation of deformation energy of a body, and I give you the equilibrium equations for a deformable body. He wanted to repeat this reasoning in the case of deformable bodies. Okay? Now, I could try to do for you all the calculations made by Viola, which could mean a nightmare of letters, pages and pages of calculations. Instead, we will not follow Viola's method. We will use the modified method, which can be obtained by using Levi-Civita index notation for the deformation measure. I must repeat this for you, because you must understand that the tools are essential in getting results. So, what for Viola was a revolutionary result obtained after painful calculations he got a prize for it. Okay, now it becomes easy. We can teach it to students. Why? Because we have found the best way for teaching it, the best way for understanding it. We have found the conceptual tools which are the most appropriate for teaching this thing. Which are the most appropriate tools? Tensor notation with indices, Levi-Civita notation. The tensor GAD, in my opinion, should be named after Piola. I don't know, I will look for in the literature. This is introduced by Piola in his paper of 1826. You know how he wrote this? We are writing in this way. G11, G12, G13, G22, G23, G33, and I'm not repeating here because it is symmetric. Okay? I don't know why. You know, he was very clever, but he could not invent tensors. You know how he represented this G? You lose completely the structure of your tensor if you write this way. And your calculations become a nightmare. Especially if you don't write F. No, we wrote X1, X capital 1, X capital 2, X capital 3. Okay? And X2 and X3. And Piola wrote X of A, B, C, Y of A, B, C, and zeta of A, B, C. Then imagine how difficult it is to write T1 in terms of the derivative of the x, y, and z. It soon becomes a terrible set of equations. Simply because you are not choosing the correct notation. So notation is everything. When I was a student and I started my PhD, my professor spent 3 weeks for choosing the notation. I thought he's crazy. I believed he had a mental disorder. And instead, he was right. He wanted to look for the right way for introducing the names of the objects which we needed in order to make the calculations easier. Okay? If you understand index notations, you suffer 2 weeks. Then your life will be easier. If you refuse to suffer 2 weeks, you will suffer the whole life. Or you will not do a good research. This is obvious. Okay? Okay, so we stop here.